Okay, so good evening, everyone, and welcome to tonight's VKC seminar. My name is Amy Maley, and I'm a master's student here at the University of British Columbia, and I'm this year's VKC host. And I also have with me here Maya Kopolova, who is our convener. VKC is a series of seminars for diamond geology and related topics, and our goal is to bring academics and industry professionals together. I would like to acknowledge SRK Consulting for being a long-standing VKC sponsor. And just a few quick Zoom housekeeping notes. Please make sure that your microphones and your cameras are turned off throughout the duration of the presentation, just to ensure good quality of streaming. Our presentation will be about 50 minutes long tonight, so please keep your questions till the end, at which point I will help to facilitate a question and answer period. And I would also like to share a quick slide here just as a plug for Barbara and the 12th IKC. Registration is going to be opening for that in July. So just put that in your calendars and go to their website if you want some more information about that. And without further ado, I would like to introduce today's speaker. So our speaker today is Balz Kamber. And Balz is currently a professor at Queensland University of Technology. He's a mineralogist and geochemist, specializing in interactions between the lithosphere, hydrosphere, and atmosphere. He completed his PhD at the University of Bern, where he conducted research on the tectonic and metamorphic evolution of the Limpopo Belt in southern Zimbabwe, and has since continued to contribute to research on cratons. Balz has held positions in the UK, Australia, Canada, and Ireland, including a Tier 1 CRC in Precambrian geology at Laurentian University. Throughout his career, he has contributed new ideas to the origin of garnet and silica enrichment in cratonic harzburgite, and today he's going to be talking to us about G10 garnets. So I will let you start sharing your screen here, Balz.
Is it shared?
Yeah, looks good.
Okay, wonderful. Good evening, everyone. Thank you, Amy, for an excellent introduction and for hosting me, Maya. I won't waste any time with further introductions, and let's just get started with my new look at the origin of G10 garnets. As I wasn't completely sure on the background of the audience, I thought I might break down the presentation into four topics, of which the first one is the most important for today. Now, in each case, I may go a little bit deeper than some of you would like, but I hope that once we've finished one topic, we can start with the next topic and you can jump back on board. So first, I'm going to just talk a little bit about existing ideas about G10 garnets and where they might have formed and where they might have come from, and then present to you our new model. Then I want to move on to what the model might tell us about the ancient continents, the cratons, way back in the past, and I'm going to propose a connection to a different rock type, not the harzburgite, but actually a volcanic rock called komatiite. And then we'll get to the third point. Is there any practical application, for example, for diamond exploration of these new ideas? And I need to warn you, it was an academic project, so it was never designed to have any particular practical application. And finally, we'll end up with something quite speculative. I want to address this question of why might diamonds have formed in the hottest part of the ancient mantle, given that they like it cool. I'm going to start now recapping the well-established connection between ancient cratons, elevated shield areas, typically Archean in age, and their deep seismically visible roots, shown here in these purple colors, where essentially pretty much the deepest parts of the existing lithosphere, continental lithosphere on Earth, is always sitting under what is Archean crust. Not all Archean crust has got such deep roots, but the majority do. And certainly kimberlite passing through such deep cratonic lithosphere is disproportionately endowed in diamond. One thing to note here is also that komatiite, that ultra-mafic, very magnesium-rich volcanic rock, is pretty much restricted, with a few Paleoproterozoic and Cretaceous exceptions, also to occurring on the surface of these Archean cratons. So, however, it is, of course, you know that a lot better than I, true that not every kimberlite that passes through such deep cratonic Archean roots carries diamond. And there are many reasons why that might be. I've just put 3 on here. Maybe a kimberlite carried diamond, but during the emplacement, the diamond was destroyed through oxidation or whatever. Or the kimberlite might have passed through a deep root that once did contain diamond, but even down there, the diamond had been later destroyed in events that followed the original formation. And thirdly, the kimberlite might have passed through barren but deep root that should potentially be prospective. And it's that third possibility that I was particularly interested in. Of course, you all know that we use the help of other minerals that are known to liking to coexist with diamond in the search for prospecting for diamonds, and garnet is obviously one of the most widely used mineral. And here in this hand specimen, you see that obviously just from color, we can see eclogitic versus peridotitic garnet xenocrysts. But it has long been known that you can use the chemistry and relatively simple major element chemistry of these minerals to estimate diamond prospectivity. And one of the most widely used of these chemical indicators is the G10 garnet. In reality, it is strongly associated as an inclusion, silicate inclusion in diamond. And for the sake of simplicity, we just want to point out that G10 garnet is unusual in being very low in calcium concentration, but surprisingly high in chromium concentration. So if this was a first year geochemistry lecture, I would say we shouldn't be too surprised, because when we compare the chemistry of the continental crust with that of the mantle, we find that the continental crust likes its calcium, whereas the mantle likes to get rid of the calcium, whereas the mantle likes to hang on to the chromium, and the continental crust is therefore poor in chromium. So sort of very qualitatively, we can say that G10 garnets must therefore be from mantle areas where melt has been removed. But that's of course not nearly good enough for us to get a better understanding of what they mean. So the next thing before we turn to modeling is we can look at experiments. There are experiments, and I applaud the people who conducted and continue conducting these experiments for their persistence, because these are difficult to conduct. In particular, I'm just pointing out one example, maybe the most widely used set of experimental data by Mike Walter from 1998, melting of garnet peridotite and the origin of komatiite and the depleted lithosphere. So if you look at these two tables on the left, you see that Mike used a starting composition containing 3.45 weight% calcium and 0.41 weight% chromium oxide, and all his liquids that he generated, I just picked out one that corresponds to a depth of about 220 kilometers, produced liquids, so melts, with much more calcium than the original mantle and a little bit less chromium than the original mantle. So obviously, Mike produced experiments with variable percentage of melts, and that leaves behind some silicates, including, of course, garnet. So it would be logical that we simply compare the compositions of these garnets produced in those experiments with those that we find in peridotites and as diamond inclusions. And I've just picked out one suite here, but you could take the entire suite that he published. Again, conducted at 6 gigapascal, so about 220 kilometers or so, and with increasing temperature from the left, 1670 to 1755 degrees Celsius. And what you can see is that with increasing temperature, the calcium content of these garnets goes from 4.4 to 3.9 weight%, and the chromium concentration stays pretty much between 1 and 2%. So if you plot these compositions of these experimental garnets into the classic classification diagram, you see that none of those come anywhere near the composition of G10 garnets. And this is really fundamentally one constraint that has led to the current belief that it is not possible to make such G10 garnets at the depths that they were encapsulated into diamond, or at the depths that we know the current cratonic garnet peridotites now reside on the current geotherm at, say, between 4 and 5.5 gigapascals. So this was a puzzle and continues to be a puzzle. And one solution to this puzzle was originally proposed by Dante Canil in 2004. Dante also conducted experiments and compiled data from other existing experiments where he looked at the capacity of peridotite after it has lost melt to retain chromium. So on the left-hand side diagram, you see 4 suites of experiments. Shallow in black, 1 gigapascal, so 35, 40 kilometers, 1.5, 3 to 4, and greater than 4 gigapascals. And on the y-axis here, we simply have the chrome to aluminium ratio, where if we have a high ratio, we have capacity to retain chromium and therefore to potentially make chromium-rich minerals. And what Dante found is that anything shallow can retain the chromium in the peridotite. Everything deep seems to lose the chromium, and therefore no hope of making chromium-rich garnets. So this then led to the idea that maybe there is a 2-stage process at work. Initially, we're melting the mantle, and to quite a high degree, but at shallow pressures, maybe, at 80 kilometers or so. And we're obviously producing a corresponding crust that sits on top of our residue, but with time, either through underthrusting or imbrication or simply by thickening the growing craton, we're pushing what is originally here, the blue circle, a spinel harzbergite. We're pushing it down to make, and we're increasing the pressure, and we're eventually converting the spinel harzbergite into a garnet harzbergite, and that therefore these G10 garnets actually originated as spinels. So there is a second line of reasoning that I'm not going to go into, but that we've covered in the paper as well. But this is one of the fundamental ideas behind the shallow origin of original G10 garnet hosting Harzbergite. Now, one thing here that is troubling is that these experiments, be it Dan Tecanil's or Mike Walter's experiments, are sort of isochemical experiments. So basically you take the original mantle composition and you heat it until you produce melt fractions of 10, 20, 30, 40, 50%. Now, this is physically, although as an experiment it's interesting, as an analog to nature, this is not realistic. This here is the same table as I've shown you before from Mike Walter's experiments, where he went from 0 to 41% liquid. Now, the reason that is unrealistic is that it is not actually physically possible to retain so much liquid at depth, because the liquid at depths above 350 kilometers is quite a bit less dense than the peridotite, and therefore, as you're starting to form liquid, let's say 10% liquid or 11 like in this experiment, this liquid wants to escape and it travels up and gathers velocity, and it eventually erupts as a volcanic rock. So in reality, therefore, we cannot compare the outcome of experiments with such unrealistically high liquid concentrations with what we're looking at in terms of garnet and spinel Harzbergites retrieved from cratons. And up until now, there are no actual experiments that would allow us to make a more direct comparison. But what has become possible is that we can make hypothetical such experiments because we can now use a predictive thermodynamic model to see what would happen in an evolving system. And so this is all based on thermodynamic data put together by the Cambridge and University of Melbourne group with additional input from my collaborator, Emma Tomlinson, specifically producing a model suitable to predict the relationships of compositions of solids and liquids when you melt peridotite. And my former master's and now PhD student, Carl Walsh, his MSc project was to essentially explore what would happen in a mantle where we start extracting these liquids and continue melting. And this was published earlier this year. And the title of the article was "Deep Ultra-Hot Melting Residues as Cradles of Mantle Diamond." So what was the idea? So on the right-hand side, you have a diagram where you see temperature on the horizontal axis and the abundance of the minerals on the vertical axis. So this here would just be a normal leusolite where we have olivine, garnet, and clinopyroxene at 1650 degrees. And this essentially models what the experiments have performed, be it Dan Tecanil's or the Japanese experiments. And what you see is with increasing temperature, the amount of liquid goes up very rapidly. So what we did is we said, well, after 16.67%, producing 16.67% liquid, instead of heating this, we're extracting this liquid and we're making a new solid. This new solid has now a different composition than the original mantle, and we do that 3 times. We extract 3 lots of liquid and look what happens to the mineral compositions that evolve in such a dynamic mantle environment, because we feel this is a closer approximation to what must have happened at least under some cratons. And essentially, what you get is like what happens when you triple distill a whiskey. Your first distillation is quite rough because it coexists with a lot of stuff that you don't want in your whiskey. But as you distill and distill and distill, the distillate gets ever finer. So this is shown here with what happens to calcium. So our starting composition has 3.58% calcium, but once we've extracted the first liquid, because the calcium goes into the liquid, the new starting composition is much lower in calcium, and so on. So that you see that once we've taken our third batch of liquid out, our residue is now very low in calcium. Meanwhile, chromium is increasing by a little bit. And this has actually dramatic influence on the composition of the garnet. And I've shown this here more schematically. Essentially, the first garnets that we form are indeed not G10 garnets, but because we're extracting this calcium and chrome poor liquid and making our system calcium poor and chromium rich, the garnets that we produce wander very nicely into the G10 field, be it at 4 gigapascals, 5 gigapascals, or deeper. I should warn you here, we cannot really model these relations any deeper than corresponding to about 200 kilometers because there aren't enough experimental data at the moment. What we see here on the upper panel is essentially temperature, and then the proportion of garnet in our Harzbergite. And what you see is how the garnet proportion crashes down here, seen in the thickness of this garnet field, but garnet does persist to 1870 degrees. So we're having less garnet, and as the garnet is coming down in modal abundance, the stippled line here is the chrome concentration. Chromium oxide concentration goes up very high just as the garnet exits. This residue here would be a garnet dunite. So essentially, this allows us to compare the chromium concentration and calcium concentrations in these modeled garnets with actual garnets from garnet Harzbergite xenoliths here in the orangey color, where we have probability on the y-axis and chromium concentration on the x-axis, and we see this sort of mode at roughly 6 to 7 weight% chromium oxide in the xenoliths, and more chromium-rich composition in general in the diamond inclusions. And here are two of our models. I'm not going to go into the details of the various models, but essentially our model is now able to predict chromium concentrations of up to 18 weight% Cr2O3, very similar to the most extreme ones in the diamond inclusions. So this takes me then to my first conclusion. G10 garnets, when, how did they form? They did not necessarily form in the shallow mantle. They could have formed at 175 to 225 kilometers, but if they did form down there, they must have formed at extremely high temperatures, 1750 degrees Celsius or higher. So I'm not going to argue that all chromium-rich G10 garnets formed that way, but I'm going to make the case that it is possible to make them down there despite the earlier interpretation of experimental results. We are currently conducting new experiments in these more refractory compositions to see whether we can emulate these conditions and produce experiments that are more relevant to Harzbergitic cratonic xenoliths. So now I'm going to move on to the second question, where I'll spend less time on. What does the new model tell us about the ancient continents, cratons, way back in the past? And I'm going to try to make the point that we might want to connect these G10 garnets to the occurrence of komatiites. So what are komatiites? Komatiites, as I said at the beginning, are nearly uniquely Archean volcanic rocks. They exist as lavas or as sills and dikes, like you see here on the right. And they are extremely olivine rich. They must have more than 18% MgO, magnesium. Typically, they have 25 to even 38% MgO. And they're quite conspicuous in the field when they're well preserved, because they make these beautiful olivine spinifex textures, which we don't have to go into the details for. What I do want to note is that these komatiites also come in a variety of sort of classifications, so groupings. And the grouping is provided again on a chemical basis, a little bit like with the garnets, where we have the G10s, G9s, G8s. Here we're using aluminium and titanium. And basically here I'm showing you a histogram of the aluminium titanium ratio in worldwide komatiites. I should say that there are hundreds of thousands of komatiite analyses. The reason is that komatiites are very often associated with Archean nickel sulfide deposits, and with platinum group element deposits. So there is a lot of exploratory lithogeochemical data available. So what we see here is essentially that most komatiites, the dominant group of komatiites, have an aluminium to titanium ratio of 20 and plus or minus 4 or 5. And these are called aluminium undepleted. Then there are the aluminium depleted komatiites. They have a low aluminium titanium ratio, and this is generally interpreted to mean that they had garnet in the source. And then the distribution falls away to few occurrences of very high aluminium titanium komatiites. The most extreme ones are called titanium depleted, and the ones between sort of 25 and 40 are called aluminium undepleted. People disagree about what this might mean. It probably means that an aluminium-bearing mineral, such as garnet or spinel, was melting and contributed aluminium to this melt. I'm going back one slide and point out that these experiments, be it from Walter or Dante Canil, they all produce aluminium depleted komatiites with low ratios of aluminium titanium. So these here are the ones that were made in the experiments. And again, from that point of view, what we have to conclude is that the experimental komatiites are not a match for the ones that we see distributed on the in greenstone, in Archean greenstone belts. So we wanted to explore in that paper whether there was a way of connecting the komatiites with the G10 garnets. And so this is a slightly complicated diagram, but it is an important diagram nonetheless. So on the left-hand side, we have magnesium concentration in a komatiite versus the aluminium titanium ratio. And in these lines here, or these suites of points, are essentially our model results. So what we see is that with increasing temperature, the magnesium concentration of our liquids go up because we're consuming olivine in the source of the komatiite, and the aluminium titanium ratio starts to increase rather spectacularly. the important thing now is that this trajectory is color coded. So the red liquids here with relatively low aluminum titanium ratio, they all have a garnet, they coexist with a garnet that contains little chromium, less than 5 weight percent. Then the blue guys here, they coexist with a garnet between 5 and 10 weight percent chromium. And then the orange and yellow are the only ones that can coexist with the really truly chromium rich G10 garnets. So if we took a cutoff value here of say 10 weight percent chromium, then essentially what that means is that G10 garnets that contain more than 10 weight percent chromium were in equilibrium, so coexisted with chromatites that sit here. And that tells us that there were only few chromatites erupted on the Earth's surface that could have coexisted with such G10 garnets. So of the hundreds of thousands of lithogeochemical data for chromatites, those with that could have coexisted with these very chromium-rich garnets are very rare. They only make about 7.5% of the erupted chromatites. So this then informed the final step of our model, where essentially we, based on the relative paucity or dearth of aluminium-rich and titanium-poor chromatites, we postulate that most of the mantle, this is a cartoon here, depth through the cratonic lithosphere, most of that mantle is not sufficiently melted or was never sufficiently melted to contain G10 garnets. G10 garnets we envisage to have formed in only areas that were repeatedly remelted at least twice, but possibly 3 times. And these seem to have made preferential cradles of diamond. So these apparently were the zones that were most suitable for later formation of diamond in them. So that takes me then to the conclusion number 2. What does the new model tell us about the ancient continents? What is the connection to chromatiite? We would argue that most of the cratonic root is a residue after moderate degree of melting and not extreme degree of melting, as is implied also by the corresponding volcanic rocks erupted on the ancient surface. Namely, most of these rocks are either basalts, tholeiites, iron-rich tholeiites, or they are aluminium undepleted chromatites that we can generate after only moderate degrees of melting and not the extreme degrees that our model implies for the origin of the G10 garnets. This takes me now to the third question. Is there any practical application, for example, for exploration? And I think in South Africa, there is an intriguing. South Africa is, of course, the place where chromatites were first discovered and named after the Komati River. And South Africa exposes the full variety, the full zoo of chromatites that are known. And the most interesting one for us is this Commondale chromatiite here that was described originally by Alan Wilson. And this exists here south of the Barberton Greenstone Belt, not quite a bit along the edge of the Capval Craton, and not in total proximity to the diamond occurrences in Lesotho and Kimberley and Jagersfontein, but equally not very far away. I'm not sure how familiar the audience is with a paper that Alan Wilson has published more recently in 2021 with Robert Bolhar, where he studied olivines not in xenocrysts from kimberlites, but in the komatiite erupted here in Commondale. Typically, the olivines that you find in a komatiite are fractional crystallization products. So they're sort of cumulates of olivine that forms as the komatiite is erupting. However, what Alan found is that some of these olivines have cores that are this is a traverse of chemical traverse through an olivine xenocryst. And basically here we have on the y-axis aluminium and chrome concentration. And what Alan discovered is that some of these cumulate olivines are actually xenocrysts that must have come from the mantle from greater than 200 kilometers. He's come up with a model that is very wild. I'm not sure that I buy all of it, but I do understand the reason why he is suggesting that these xenocryst cores in some of the cumulate olivines must come from greater than 200 kilometer steps. Well, the reason this is exciting is that the Commondale komatiite is 3.3 billion years old. This also happens to be the lutetium hafnium model age of garnets retrieved from the Cabal Craton megacrysts. We tried to see whether we can make the Commondale komatiite parental magma with our model, and in our model, if we melt the mantle incrementally the way I've explained and reach 1827 degrees Celsius, we can make a liquid that assumes the composition of Commondale komatiite very well, with the exception of potassium, where the observed Commondale parental liquid contains more than our model. We attribute this to contamination. But anyhow, what is important is that our model also predicts that this komatiite would leave behind a G10 garnet with 11.5 weight% chromium, which is a typical chromium concentration found in the adjacent in garnet xenocrysts and diamond inclusions from the nearest kimberlite pipes. Now, this type of ultra depleted, so this titanium depleted komatiite is not only known from South Africa. For example, Rebecca Sproul and co-authors reported some from the Abitibi greenstone belt in Ontario and Quebec. And while the Abitibi is currently underlain by a shallow mantle root, which probably has been eroded, it nonetheless, the komatiites that Rebecca described, some of them seem to suggest that at the time, so 2.7 billion years ago, there must have been a deep lithosphere, and lots of data are available that can be mined. Obviously, Abitibi would not be where I'd be looking for diamonds. But if we go a little bit further northwest into this area, the Ontario's Ring of Fire, where there is an awful lot of exploration going on for copper and nickel sulfide deposits, a huge amount of data are being generated, including for komatiites that are exclusively looked at for their nickel and copper potential. But I'm pointing out that the Victor diamond mine is only less than 100 kilometers away from some of these exploration camps. And if I had nothing better to do, I might want to look at all the the survey hosted database for new komatiite compositions that are being reported, but nobody is looking at this from the point of view of the source area of those komatiites. Intriguingly, of course, the slave craton, despite being host to diamonds, does not in its cover group contain any komatiites at all. So this was recently again studied from the point of view of the reason of this dearth of komatiite when compared to other cratons remains enigmatic. And Bill Davies, nearly 20 years ago, argued on a completely different basis that therefore it is difficult to reconcile the nature of the tectonic events on the slave with the pre-2.7 billion year development and preservation of a thick tectosphere under the slave. And an implication of their model was that diamond formation in the slave should be Neo-Archean in age. But we, of course, know that there are model ages for diamonds that are older. So in conclusion, is there any practical application? Well, given that komatiite lithogeochemistry data are typically published in provincial survey reports, it seems quite easy and inexpensive to hunt for occurrences of high aluminium titanium types that must have, at the time in the Archean, left G10 garnet at depth. So it would be an indication that G10 garnet once existed there. But of course, whether that has any diamond implication or not depends on whether the lithosphere has survived to this day and whether the crust and the lithosphere actually formed together. So this takes me to the last aspect of the most speculative aspect of the talk. How come that diamonds, according to our model, seem to form where the mantle was once at its hottest, given that diamonds like it cool? This really is something that seems very counterintuitive. So basically, the model, just looking at the garnet composition, suggests that we need the mantle that forms these garnet harzburgites or garnet dunites must have been heated to 1800 or 1850 degrees at the depths of garnet encapsulation. This is an extremely high temperature, but it is actually also borne out by the very high forsterite content, so the very magnesium-rich nature of the olivines that you find in diamond inclusions and in many xenoliths. So in order to make olivines with 94 forsterite or even 93 to 93.5 forsterite, you do need to go to these extremely high temperatures. So that's, again, a reason why we believe that the original lithosphere, although not nearly as depleted as the G10 bearing lithosphere, must have been remelted, but only locally by upwellings or intrusions or heat pipes that have, by definition, have come from greater depths. So this heat cannot be only conducted because it is not possible to make the mantle below the lithosphere so hot that you'd conduct this heat into the overlying lithospheric mantle. This can only happen if you bring in heat through advection by upwellings that contain liquids. In other words, the orange stuff that comes from even deeper is itself a liquid. And this would mean that we essentially took very deep komatiites that then interacted with the pre-existing lithosphere in what is essentially a form of metasomatism. It is essentially the interaction between a solid and a liquid. And if you look at some of the rocks that contain this garnet here contains 8.5% chromium, and you look at these textures where you have olivine, plenty of olivine inclusions in orthopyroxene or orthopyroxene inclusions in these garnets, which are centimeters big, or look at these relationships between olivine, TPX and OPX in these very refractory peridotites, at least in some of them, these look to me more igneous than metamorphic or equilibrated in nature. And it's something we're exploring at the moment. Regardless of the nature of these interactions, what is very clear is that these pipes and upwellings or plumes must have eroded a once much deeper lithosphere. And while I haven't got the time to go into this, I can at least make a plug for this paper which we published last year, evidence for a very thick cap-wall craton root implications for equilibrium fossil geotherms in the early continental lithosphere by a former PhD student, Brendan Hoare, where we tested how deep the lithosphere would have needed to have been if the mantle was hotter in the Archean as most people believe. So if we believe the mantle was as hot as Claude Herzberg likes it to have been, namely with a potential temperature of 1580 degrees, it is unavoidable that the lithosphere must have been greater than 300 kilometers deep. There is just no way around it. And it could explain some of these PT conditions that are recorded in diamond inclusions. One possibility we also need to keep in mind, and this is very speculative, is that not everything that is now in a lithospheric mantle root originated as a tectosphere, as growing together, but there might have been portions of relatively refractory, so melted out residue material that was not originally part of the craton as it formed and only got stuck into this growing lithosphere, maybe by accident or being brought up from greater depths. And I think that might be one of the reasons, that one of the possibilities one might want to envisage for the slave craton. Anyway, I do appreciate that this last point is pure speculation. But I think one thing that we need to keep an open mind about in terms of why diamonds seem to form where the mantle once was at its hottest is that the G10 garnets that were encapsulated in, at the depths of, let's say, 4.5 to 6 gigapascals were likely not then close to the base of the ancient lithosphere, but that was maybe happening in a much deeper lithosphere, and the base of this lithosphere essentially insulated these depths from advecting heat. So it must have been continually as hot. Instead, these heat and melt upwellings may have invaded this existing lithosphere as kinds of pipes and not the typical mushroom plumes that we are all familiar with, but in more localized heat pipe heating. The residues of such extreme heating and melting will have very low iron 3:2 ratio, so they will have a good potential to reduce carbonate to elemental carbon. And finally, some portions of this deep lithosphere may not always have been related to the original tectosphere. So the very deep lithosphere may not everywhere have formed together with the crust that sits above it. And with this, I think my 45 minutes are over, and I thank you for your attention.
Thank you very much. That was a very interesting talk, Balz. So now I am going to open up questions for the question and answer period. You can ask me just directly over the Zoom, or you can send me a message in the chat as well. Does anyone have anything that they would like to ask, Balz? Okay, I'll start one off. I'll start with one then. When you were talking about your melting experiments that you were doing at the beginning, the stepped ones, what are the actual samples that you're starting off with? What is it that you're using?
So I should clarify that at the moment, or what we published is just models. So these are essentially approximations to experiments. But we are currently conducting such experiments in a project with the Australian National University, but also my collaborator Emma Tomlinson is running them at the moment at Carnegie with Mike Walter. And essentially the starting composition is informed by our model. We essentially model 10% or 15% melt loss, and then we're making an artificial rock from powders off a shelf, essentially. Yes. So these are not natural starting materials. Because there isn't really a peridotite that doesn't contain some contamination or some hydration or serpentine, which would be totally detrimental to the experiment. Also, in our experiments, we're spiking the powders with, or the starting composition with rare earth elements, because people want to know what's the rare earth element pattern of the resulting garnets. Yes, but they are artificial rocks. Yeah, they're tiny. They're only 2 by 1 millimeter by 1 millimeter. Yeah.
Okay, thanks. We do
If
have a
I may
question
follow- Yeah, if I may follow, sorry, Amy, I also had questions about experimental confirmation of your model. And if you're saying that your plumes or your melts are coming from great depth and you cannot, can you confirm your models with experiments if you're envisioning your melting at 500 kilometers or even deeper?
Okay, so yes. So the initial experiment is, of course, to take a peridotite, quite a fertile composition, melt it, look what is the residue, make a new experiment, melt the residue, determine the melt composition. So basically go through this stepwise process and go to a reasonably, let's say, a moderately depleted composition. Meanwhile, Emma and Mike Walter at Carnegie run multi-anvil diamond experiments at 400 to 500 kilometers to generate the liquids that would come from there. Once we have the compositions of those liquids, we will then put together these liquids with our residues in various proportions. So this is a project that's going to take probably 5 years.
Mm.
Yes, because as you rightly point out, it is very well to just sort of assume a composition of the incoming liquid from great depths, but we have very poor understanding of what these liquids would be in composition, particularly with regard to the trace elements.
Mm-hmm.
Yeah, but it's critical that we do these, and unfortunately they're not trivial, and you have to run a lot of experiments. But thankfully we have funding for both types of experiments.
Mm-hmm.
We have, however, been able to make some G10 garnet already. So we have made, it has only got 7% chromium, but the point of our prediction or the model is that only when you make when you are left with the least amount of garnet, a few percent, then it becomes very chromium rich. And of course, it's very difficult to hit exactly that temperature in the experiment, because you can then also make a donite where you have no garnet left. And so it's a bit frustrating because you can't watch the experiment.
Okay, we have another question in the chat here from Jonathan. He would like to know, have the trace elements in your melt models been investigated? And if so, do those profiles agree as well?
So yes, Jonathan, very good question. We have only modeled the rare earth elements. No other elements have been investigated. And yes, the rare earth elements, we can produce the lutetium and ytterbium trends that are seen in progressively depleted garnets in Harzbergites. And the reason we can actually model this quite accurately is that thermocalc, the model that we use, yields stoichiometric melt reactions. So it will say our first melt reaction consumes this much CPX, clinopyroxene, this much olivine, and this much garnet, and it produces this much liquid with this much new orthopyroxene. And therefore, for the first time, these models allow us to do proper dynamic incongruent melt reactions. The biggest unknown is actually about the partition coefficients. So the extent to which these trace elements are shared between the various minerals and the liquids at such high temperatures, because no previous experiments have ever explored this, which is why we are spiking our starting powders with these rare earth elements and some other elements. But yes, so to the best of our knowledge at the moment, yes, we can reproduce the loss of heavy rare earth elements, which has always been argued as a reason why the G10 garnet couldn't have started as a garnet, but was originally a spinel.
Awesome. It looks like Maya has another question too.
I feared as much.
I have several questions, and let's start with the ambient geotherm, or we should probably not even call it a geotherm. So everything which is below 300 kilometers should be adiabat. So, and you said it's plume, yeah? So it's not ambient adiabat. So it's plume related, and you totally expect it to be 200 degrees higher than the normal ambient adiabat at that depth. So then, but at the same time, you said that if we're looking at the plumes, we're envisioning strange plumes with already melting started. So you have like, I don't know, channels of melt already, rather than normal solid plumes like thermal upwelling, but not molten upwelling. So what can you tell about, is it really should be 200 degrees increase with respect to the ambient adiabat?
So you obviously bring up a very good point, and I tend to not call them plumes for the reason that most geoscientists who have been taught about plumes, they think of these solid upwellings that then mushroom out to this lava lamp plume environment. And that is, of course, in a mantle where the plume originates really at the core mantle boundary. I envisage these heat upwellings or heat pipes to originate at the former base of the upper mantle. So basically, I envisage that during the Archean, there was a thermal boundary layer, a barrier in the transition zone, and that heat from the lower mantle and specifically from the core accumulated below this mechanical boundary layer, and that occasionally sufficient heat was accumulating in there so that you melted the base of the transition zone. And these upwellings or these pipes are essentially liquids that emanate from the base of the transition zone. I know that this is completely crazy, but I think that the breakdown of this barrier, and I'm not the only one, there are about 3 more such crazy people, believe that the breakdown of this barrier marks the Archean Proterozoic boundary. That during the Archean we had a barrier, and after the Archean we no longer had a barrier, and that therefore we really couldn't generally make komatiite anymore. So it would be a major reorganization event of the convection system in the mantle. So there's a model by Jeff Davies, I think it was published in 2008 or 2009, where he envisaged the subduction of oceanic lithosphere to never penetrate the transition zone and to build up garnetite in the transition zone, and that barrier was essentially piled up garnetite. Others, Breuer and Spohn, in a Nature paper that nobody nearly actually cited, I think from 1996, they believe that maybe it was a leftover from the magma ocean crystallization. I just basically appeal to a thermal boundary layer or a mechanical boundary layer as well, which we lost at the end of the Archean, and that was the source from which these more focused upwellings or pipes emanated. Yeah.
Mm-hmm. Okay.
It would also allow you to bring up lower mantle or transition zone minerals and place them into the shallower lithosphere. But yeah, but
well,
yes.
Yeah, we can bring the low mantle material even without melting. If it's slow advection without melting in a plume, we'll get the same effect. And yeah, it's just 1800 degrees. It's such a high, unrealistically high temperatures that so above the normal adiabat. So that's why it's just just begs the question. Amy, do we have more questions from someone? I don't want to hog the time.
We don't have anything in the chat right now. Maybe I'll open it up to see if anyone else has anything that they'd like to ask. Going once, going twice. Doesn't look like it.
Okay, so then I'll ask my second question, and that's about your triple distillation. That's a nice term for that. So then if you think about the complementary melts for the triple distillation, you should start with basalts, then go to picrites, and then go to komatiites. So did you try to find such sequences that would start with early basalts and continue to younger komatiites somewhere on the cratons?
So I should say that, interestingly, at 5 gigapascals, so at relatively great depths, you don't actually make a lot of basalt. even within 50 degrees of heating, you're already in picrite, and very quickly you're in komatiite. If you go even deeper, you know, if you look at the early Japanese experiments from Takahashi, 6% melting at 10 GPa already makes a komatiite. So because you consume a lot more olivine. But what I should say, we have started looking at the sequences of komatiites and basalts in many greenstone belts, and the basalt is not related to the komatiite. So the basalt is not, we cannot construct a liquid line of descent. And in certain greenstone belts, particularly in Barberton, you do see the sequence of originally aluminium depleted to undepleted to enriched. So there we can construct the liquid line of descent that is predicted by the triple distillation. But in Abitibi, for example, there it seems totally random. This has also surprised me, and that is part of the reason why I think that these this melting might be quite localized and isn't, a massive plume that is sort of lithosphere wide, because I agree with you, the prediction would be from a mass balance point of view that we would get the first distillate, the second and the third. And it's one thing that you should also be aware of is that these aluminium enriched and titanium depleted komatiites, they had eruption temperatures of 1700 degrees. And if you look in Commondale, a flow is 1 centimeter thick because it was so liquid. And I think there is a tendency maybe of some of these are maybe overlooked. They, of course, are strongly serpentinized, and I think they're underrepresented in the global databases. But there is not a global trend, shall we say. So that's part of the reason why I think maybe this melting is reasonably localized.
Mm-hmm.
Do you have anything to comment on that, Maya?
No, yeah.
No. Does anyone else have anything that they'd like to ask before we stop recording? No. Okay, well, I am going to end the recording.